Hello, welcome everyone. Welcome back to my channel. Today we are going through the AQA past paper questions. It's actually the past paper of 25th May 2023, higher tier paper 1. Let me see the question number 1. Question 1 shows how the national grid connects a power station to consumers. Complete the sentences. Transformer X causes the potential difference to. See, first of all, in a national grid, let me explain you one thing. A national grid is basically a whole setup that is used to provide electricity because power stations are producing electricity. But then they have to distribute this electricity to the household. That's why they are producing it. So for that, when it's produced, the current is pretty high. The value of current is very much high when the electricity is produced. And in that case, if you will supply directly, suppose we are not using transformers at all. From here, if you will supply directly through the cables to the household or to the consumer's place, then there are high chances are definitely what will gonna happen is that these wire will burn out because of the production of high amount of heat. We know that power is I squared R. That means more is the current and squaring it. That means higher the current, the higher the power will be generated, higher the heat will be generated, and the wires can get melted. That's why we use the transformer. That's why the first transformer, that's called step up transformer, is used. This is actually the main important thing is they are used to decrease the amount of current. If you decrease the amount of current then to the safety level, then the electricity can be distributed through the cables without them being burned or melted. And obviously, but in doing so, if you are decreasing the current, you are actually increasing the voltage when you are using the step up transformer. This kind of transformer is called step up transformer. So the main aim is to decrease the amount of current, but in doing so we are actually increasing the voltage. When we increase the voltage, now if you are not using this transformer, you have supplied electricity, okay, it's safe, it's going safely through the wires, but what if the voltage is very high and when you supply, these all appliances are not designed for that, and obviously they will get like burst, and there are high chances of all that calamities, you can say. So accidents, sorry, not calamities, accidents. So in that case we need to lower down the voltage. So that's why before the consumer's place, a step down transformer is used in order to decrease the voltage to the safer limit, which is 230 volts in UK. So we can say transformer X, what's the main purpose? To decrease the current. So causes the current to decrease, and while doing so, and that's why it got its name step up. It's actually increasing the voltage, so potential difference is being increased. So you can say to increase. Next is which equation link the power, current and resistance, which is P is equals to I squared R. So let me show you one thing so that you can easily understand everything. And it all starts with the basic definition of potential difference. What is potential difference? Potential difference is basically the difference in energy, or you can say the energy carried by each charge. Obviously this is, take the basic setup. Okay, now when current flows, this battery is actually, if there is no battery, no power supply, there will be no current flowing through the metallic wire. But when you apply this one, when you supply the energy, the current will starts to flow. So this energy difference is given by the battery. That's the potential difference in energy. But after taking the energy, like electrons takes the energy and then they starts to move basically. So the maximum energy they take up and then they starts to move. So they are doing work. That's your potential. So electrical potential is basically energy carried by each charge. So higher the energy, higher difference is higher potential difference. So we can say potential differences, which we denote by V, is energy over charge, energy carried by each charge or work done by each charge. From here I can say if I cross multiply energy, electrical energy is V times Q. We know power is equals to energy over time. This is universal. We can apply it in mechanics, or in anywhere. So power is equals to energy over time. So energy is VQ over T. Q over T is charge, rate of flow of charge is current. So P is equals to VI. So see, from the basic definition of voltage, potential difference, we got the electrical energies formula, then electrical power formula, and one more thing. If in the question V is not given, so we can replace it, or I is not given, we can replace it by Ohm's law, which states that V is equals to Ri. So I can replace V with Ri. So P is equals to Ri times I, and this will give you Ri whole square. So don't just rely on the formula sheet and everything. Obviously, these are very basics to understand the concepts. So P is equals to Ri squared, which is this one. Moving on to 1.3, a transmission cable has a power loss of 1.6 into 10 to the power of 9 watts. The current in the cable is 2000 amperes. Calculate the resistance of the cable, and that's why we just saw that power is equals to I squared R. And if power is equals to I squared R, I is 2000, so is equals to 2000 whole squared, and resistance is 1.6 into 10 to the power of 9. I'm sorry, we have to calculate resistance, I'm extremely sorry. And this is times R, and this is power, which is 1.6 into 10 to the power of 9. From here, resistance is 1.6 into 10 to the power of 9 over 4 into 10 to the power of 6. On simplifying, we'll get 400. So our answer is 400 ohms. Moving on to the next one. Use the physics equation sheet to answer question number 1.4 and 1.5. Write down the equation which links efficiency, total energy input, and useful energy output. So again, I'll be saying don't rely on formula sheet, because this is generally a misconception why I do learn this. It will be in formula sheet. Not every formulas you'll be able to see it there, and not every concept can be easily understood by it. So understand everything. Efficiency, that means if I'm supplying 100 joules of energy, obviously I'm expecting it to be converted maximum as possible. If I'm giving 100 joules of energy to any appliance, I really want that 100 joules in return as a work. But if it's not happening, at least like theoretically it's possible, but practically 100% of conversion is not possible, but at least I want it to be 99, 98. So this shows the efficiency of something. Like say for example, for a man, you have given a work and you want it to be completed in 2 hours, and he has completed in 2 hours or like earlier to it, you'll say he is efficient. So that means whatever you are giving, like if you are giving money to him and he is doing that kind of work to your expectation level, that's the efficiency. Similarly, if energy is being provided, we want the maximum energy to be converted, and that's how we can calculate efficiency. And from there we can understand that efficiency is equals to useful power output over total power input. That means you are giving up input power and you want the maximum to be converted, and this shows the efficiency. If suppose 20% is being converted, so efficiency will be 20% obviously, and you can say that particular appliance is not very efficient. Now 1.5 says the total energy input to the national grid from one power station is 34.5 gigajoules. The national grid has an efficiency of 0.0992. Calculate the useful energy output from this power station to the consumers in gigajoules. Okay, so because your answer should be in gigajoules, so we need not worry on conversion. So directly I can say efficiency 0.992. We have to calculate total power output. Let me denote it with O. And input is 34.2. On cross multiplying, our output power is 0.992 times 34.2, which will give you answer as 33.9 gigajoules. So that's your answer. Moving on to the question number 2. Figure 2 shows the equipment a student is used to determine the specific heat capacity of iron. The iron block the student used has the two holes, one of the heater and one of the thermometer. Before the power supply was switched on, the thermometer was used to measure the temperature of the iron block. The student left the thermometer in the iron block for a few minutes before recording the initial temperature. Suggest why. See, you can see this whole setup. There is a power supply, there is a joule meter, there is a heater, and iron block and a thermometer. So the question says that before the power supply was switched on, the thermometer was used to measure the temperature of iron block. Okay, so before the temperature rises, they want to calculate the initial value of temperature, and that's why the thermometer was used. The student left the thermometer in the iron block for a few minutes before recording the initial temperature. Before he records it, like he doesn't do like this, he just put it and measured it. He left it for a few minutes and then he read the temperature. Why? Because the thermometer temperature is same as, like, so that obviously this is thermometer takes little time to take up the temperature, okay, to read the temperature properly. It takes little time. It actually works on the zeroth law of thermodynamics, but in short you can say it works like it takes little time to reach to the temperature of that particular object for which it's measuring. Just like your hands, if you are at a temperature of, say for example, your body temperature is certain, right? Like in Fahrenheit I would be saying 98 your body temperature, and if you have touched something which is at 102 degrees Fahrenheit, so it will take little time for your hand to increase its temperature to reach to the temperature of the object. Similarly, the thermometer takes little time, so that time is given so the thermometer temperature can become the same as the temperature of the iron block and it can measure properly. 2.2. It shows how the temperature changed after the power supply was switched on. The energy transferred of the iron block between 5 to 10 minutes was 26,000 joules. The mass of the iron block was 2. Calculate the specific heat capacity of iron. See, the thermal energy is equals to mc delta T. So let me just explain you one thing. If I'm talking about the thermal energy, there are two different conditions in it when the object is increasing its temperature, when object is changing its phase. So when object is increasing its temperature, this C is called specific heat capacity. That means this value shows how much energy is required to raise the temperature of a unit block to increase its temperature by a unit degree Celsius. Or simple, you can say how much a 1 kg block required, the energy, how much energy a 1 kg block required to raise its temperature by 1 degree Celsius. Now, why it's important, every object has a specific value of a specific heat capacity. Take the example of iron block. Now, if you supply energy to it, suppose iron block is at 10 degrees Celsius. Now you have supplied energy and it has become 11 degrees Celsius. So how much energy was required? Maybe 200 joules of energy. No, this is not the correct data. Obviously, I'm just giving you an example. 200 joules of energy supplied. That means it was at 10 degrees Celsius. When you supplied 200 joules of energy, its temperature has risen by 100 degrees Celsius. So I would be saying 200 joules per kg degree Celsius is the specific heat capacity of this, not iron, any object, let's say any object, the specific heat capacity of this is 200. Similarly, there's another object and every type of material has a fixed value because every time it will take the same time, same amount of energy to raise the temperature. Now you have supplied, suppose 3000 joules of energy to this material to raise its temperature from 10 to 11. So that means the specific heat capacity of this will be 3000. Why specific heat capacity is important? So that you can understand how good conductor of heat something is. How can easily it conduct, how can easily it absorbs the heat. Now, coming back to this question, I was saying that there are two ways by which you can calculate it. First, when the temperature is rising, that's called specific heat capacity, and there obviously the temperature is important, and in this case the phase is not changing. If it's a solid, it will remain solid, but it's increasing its temperature. There is the second case when the phase changes but temperature doesn't change. Why temperature is not changing? Because that whole of the energy that you are supplying to a particular object is going in breaking the bonds so that it can convert or change its phase. So that is calculated by E is equals to ml, and L stands for latent heat. So specific latent heat basically, or latent heat. Whereas a specific latent heat, which is L in this case, is that amount of energy required to change the phase of a unit substance. Like suppose it's an ice at 0 degrees Celsius of, say for example, 1 kg, and the water of 1 kg, but at 0 degrees Celsius, the temperature has to be same. So the amount of energy required to change 1 kg of ice at 0 degrees Celsius to the water at 0 degrees Celsius with the same mass without rising its temperature, that amount of energy is called specific latent heat. Okay, now in this question only this one is required. Energy is already given as 26000 joules. Mass is given as 2. Specific heat capacity we have to calculate, and temperature difference is you have to calculate from the graph. So it says between 5 to 10 minutes. Between 5 to 10 minutes, that means what's the temperature at 5 minutes? We have to calculate. So at 5 minutes, let me see. This is the temperature. This one. Approximately 28 or 26, you can take any value. Let me take 28. And at 10, this is, which if you go like this, a little bit upper side it would be. So yeah, like this. Somehow, which is 54. So temperature difference would be 54 times 28. So this will give you C is equals to 26,000 over 2 times 26, which will give you 500 joules per kg degree Celsius. 500 is the answer. If suppose you're not able to recall the unit, it's there, but even like outside of it, you might be thinking, okay, everything is given there already. But if sometimes you struggle in finding the units, the best way is use the formula. In most of the cases, just formula will give you the unit. How? We know E is equals to mc dt. Giving you example from this, C is m E over m times dt. E is joules, unit of m is kg, and unit of temperature is degrees Celsius, which is this one. I'm not saying in every case, but in most of the cases you can find the unit by this way. For that you should know the formula. The 2.3 says the student repeated the investigation but wrapped up insulation around the iron block. What effect will adding insulation have had on the investigation? Obviously, the calculated specific heat capacity will be more accurate in this case, because there will be less heat loss, and heat loss can really do mess in the calculation. So this is the correct one. And second one is obviously the iron block will transfer the thermal energy to the surroundings at lower rate. That's the work of an insulation. Now figure 4 shows an electrical circuit used to heat the windscreen of a car. Each resistor in the circuit represents a heating element. The 12-volt battery supplies direct potential difference. What do you mean by direct potential difference? It's all depends on the polarity. That means those that in simple word, we can say that the potential difference, the direct potential difference is in which the direction of potential difference doesn't change. Or more technical way of writing it is, we can say that the polarity of the potential difference doesn't change. Polarity, that means positive, negative, changing the direction, that's the polarity. So in case of magnets, polarity is north pole, south pole, that's called polarity. So polarity of the potential difference doesn't change. 3.2 says, write equation links charge flow, energy, and potential difference. So we just have discussed that, right? Energy is QV, sorry. E is equals to QV. That's the answer. 3.3, calculate the charge flow through 12-volt battery when the battery transfers energy of 15010 joules of energy. Same formula, E is equals to QV. We have to calculate charge, so on rearranging, it will be E by V. Energy is 5010. Always look out the units. You have to make sure that every unit should be standard unit or related with the one that they are asking in the answer. So C is the standard unit, so every other unit should be in standard. Volts is, joules is, okay, fine, then we can proceed. 5010 over V, which is 12, on solving we'll get 417.5. So 417.5 is the correct answer. Now, ice forms on the windscreen at temperature of 0 degrees Celsius. The electrical circuit transfers 5010 joules of energy to the ice. A mass of 0.015 kg of ice melts. Calculate the specific latent heat of fusion of water. See, they have specifically given the value specific latent heat of fusion. Okay, fusion, that means here it's actually melting. That's why this is called fusion. Okay. So same formula which we have discussed, E is equals to ml. So L will be E over m. Energy is given as 5010 and mass is given as 0.015. On solving, we'll get the answer as 334000. So answer is 334000 joules per kg. Now 3.5. The electrical circuit was left switched on while the ice changed from a solid to a liquid and increased in temperature to 5 degrees Celsius. Explain the changes in environment and the movement of particles as the ice melted and the temperature increased to 5 degrees Celsius. See, the first thing is, if we talk about it, says what's happening? The electrical circuit was left switched on, and while the ice changed from solid to liquid, so ice was basically the solid first and then has become the liquid, and even though the temperature, it was 0 degrees Celsius of ice, then it will first convert into 0 degrees Celsius of water, and then it will convert into 5 degrees Celsius of water. So what's happening? First solid is changing into water, and then water has risen its temperature. So we have to talk about the arrangement and the movement of particles. So first thing is the particles. Let me describe the particles of the ice, which is a solid. So particles in the ice are regularly arranged. Okay, they are stacked over each other. The distance among them is very small. There's hardly any degree of freedom. They can't move. They can only vibrate at their own place. So first thing is about the solid, I can say particles and solids. This is a regular pattern. First thing is it's a regular pattern. Second part is distance among them is small. Distance is small or like almost negligible. So they have no degree of freedom. They can only vibrate at their own place. Since they can only vibrate at their own place, that means when they take up the energy, that this clearly shows that the intermolecular bond is very tight, it's very high, or you can see intermolecular bond is very much strong. So this suggests intermolecular force as a strong. And then we have to describe the arrangement of liquid. So liquid is let me describe the arrangement of liquid, and then I'll be describing how the arrangement will change from solid to liquid. So liquids particles are irregularly arranged. There's no regular pattern. They are just randomly arranged, and the distance, there has some distance, so they have some degree of freedom. They can move. from one place to another. They don't move too much, or the distance is not too much as compared to gases. Like in gases, the particles can move away from each other, but in liquid they can revolve, rotate around each other. And third is the intermolecular force is comparatively weaker as compared to solid intermolecular force. So we have seen the arrangement of particles in solids and liquid, and let me see, because they specifically mentioned, explain the changes in the arrangement and the movement of the particles as the ice melted and temperature increased to 5 degrees Celsius. That means you can say as the ice changes to water, the temperature remains constant. That's the important thing. If I'll show you a graph, it would be easier to understand this. This is ice. Suppose ice is at negative 5 degrees Celsius. Obviously, the temperature will increase and ultimately it will change its form and becomes ice at 0 degrees Celsius. Now, when ice melts to water, this phase remains same. The temperature remains entirely same. Only the phase changes in that case, because all the energy that we are supplying will be utilized in breaking the bonds, because we have seen the intermolecular bonds of the solids are pretty much stronger as compared to the liquid. So we have to break the bonds, and that energy breaks that bond. Instead of increasing its temperature, the bonds are being broken, and then finally it will convert into water at 0 degrees Celsius. Now, because the ice changes to water, the potential energy of the particle increases. So what happens? Potential energy increases. Now, as the water warms, the particle move faster. They gain more kinetic energy, and as you provide more energy to the water at 0 degrees Celsius, the particle gains that energy and converts it into kinetic energy. That means the particle starts to move faster, and in this case we can say the internal energy of the particle increases. Internal energy is kinetic energy plus potential energy. And then the temperature of this water increases to 5 degrees Celsius. So this is what happens in this whole process. So these were the questions. The rest of the questions we'll be doing in our next part, and I'm trying to explain you things as much as possible, and from the next video I'll try to cover the theory along with those questions and some related questions as much as possible, so that in these 3 days we'll be able to cover as much as we could, and so that you all guys will give your best in your paper. And also I'm running one-on-one classes. I'm running group classes as well from 24th of May to 31st of May. It will be the quick revision classes for your physics paper 2 and maths paper 2 and 3. And do trust me, I always did so and got the best results. So if you're looking for, just email us at exactacademy@gmail.com, and then we'll coordinate accordingly. First class is demo, totally free of cost. So that's it for today. Bye. Take care.